In this video, we're going to talk about sequences. So a sequence is just a function that has a domain that is the natural numbers, so the numbers 1, 2, 3, and so on. And intuitively, we think of this as an ordered list. So when you plug in 1, you get out the number a sub 1. When you plug in 2, you get out the number a sub 2, and so on down the line. So even though we said that this is a function, we don't use our standard function notation. We wouldn't write a of n. We typically write this a sub n, like we've written over here in the list, to denote the function instead. Okay, so let's just do an example of just computing out some terms of the sequence. So this one asks us to find the first 5 terms of this sequence, the -1 to the n over times n squared. Unless you're told otherwise, assume that the sequence starts at 1. Could start at other places. For sequences, we generally assume that you're not going to have domain issues. So if you see some value of n that's going to make the denominator 0, say, or negative under the square root or something along those lines, assume that you start at some n value that's bigger than what causes that domain issue. We're not going to have domain issues as far as sequences go. All right, so your first term of the sequence here, plug in 1, plug it into the exponent, plug it in down here for the n squared, you get -1. Plug in 2. Notice in this case you get a -1 squared, so it makes it positive, and then 2 squared is 4. Looking at the next few terms, you get a -9, a positive 16, you get a -25. You're getting those squares, and then it alternates between negative and positive. This is referred to as an alternating sequence. You'll see alternating sequences pop up when you talk about series in Calculus 3. Another way to denote sequences is as sets. So rather than using this quasi-function notation, if you will, we might put that general formula for the nth term of the sequence in set notation, and then use these. I'll just call them limits, kind of this upper limit and lower limit. This one tells you where it starts at 1, and this one tells you where it goes off to infinity. Or you might see the first one's explicitly listed out, and then the general term, and then the and so on part here representing that we're going off to infinity. All right, in some applications, you'll need to figure out what a general formula is for a sequence. So let's see if we can do that in this case. Notice that for the sequence, the terms of the sequence that we have here, each of them have a 3 in it. So we'll kind of just think of factoring that 3 off, if you will. If we did that, we'd be left with a 1, a -1/2, a positive 1/4, a -1/8. Ignoring the negative signs for the time being, notice that we're increasing the power of 2 on bottom, right? You have a 2 to the 0, a 2 to the 1, a 2 to the 2, a 2 to the 3. And then we also have this alternating bit here. So that alternating bit we saw in the previous example can be achieved from using a -1 to the n. So playing around with some things, maybe we'll start this sequence at 0 and say we have that kind of that 3 factored out idea, the 3 times -1 raised to the nth power, and then our n goes 0, 1, 2, and so on. Okay. And that certainly matches up with what we have. That's not the only option we have. Like I said, we have that alternating bit, so you could make the alternating bit come out, and you don't have to use a -1 to the n. You could be clever and use a trig function like this. Notice in this case, if you put in 0 for n, you get cosine of 0 as 1. If you put in 1 for n, you get cosine of pi as -1, and so on down the line. This cosine of pi n is doing the alternating piece. Or if you really, really want your sequence to start at 1, and your exponent needs to start at 0, I could put an n-1 in here and do the same thing. There's lots of different ways to represent the same sequence with different looking functions. One of the big topics, I would say, that we are interested in with sequences is being able to take their limits. The only limit that we're interested in for a sequence is the limit of as n goes off to infinity. The rest of the sequence is just points, right? It's you plug in 1, there's not anything around 1. You plug in 2, there's not anything around 2, right? So the only thing that we're interested in is for a limit is going off to infinity. So in lots of cases, we're going to use the same types of techniques that we used in Calculus 1 for calculating limits. So in this one, we've got n squared over 3n squared plus 5. One of the big techniques we had was divide top and bottom by the highest power of the variable that you see in the bottom. N squared certainly is the biggest power of n that we see in the denominator. So we'll divide everything by n squared. And then we can use our limit laws to break the limit up into each of those pieces. And then do a little simplifying. And then we can actually calculate some limits. Certainly the one on the top and the first one on the bottom, those are constants, so you get 1 and 3. And in the second one at the bottom, the n squared gets really, really big as n gets really, really big, so the fraction gets really, really small. So the limit goes to 0, and we get 1/3. When we say that the sequence converges if the limit exists and is a finite number. So in this case, this is a convergent sequence, and it converges to 1/3. Let's do another one here. Let's look at the limit of c sub n equals log n over n. All right, so this is one of the, we can't really do the same thing we did before because it's not a polynomial on top, but we do remember using L'Hopital's rule back in Calculus 1. Notice that as n goes to infinity, the top and the bottom go off to infinity, so that is an indeterminate form. And that is the right indeterminate form, infinity over infinity. So we can use L'Hopital's rule to evaluate the limit. So whenever I use L'Hopital's rule, I always put a little L' over the equal sign so that you know that's what I'm using from one step to another in a limit. We take the derivative of the top as 1 over n, derivative of the bottom is 1. So that just gives us 1 over n when we simplify. And that limit goes to 0. So again, we have a convergent sequence here. All right, so now let's look at this one. This looks a lot like the first example, except that now we've put an alternating term in. We've got that -1 to the n times then the sequence n squared over 3n squared plus 5. All right, so if I take the absolute value of the terms, make the alternating piece go away, then the terms go to 1/3. We saw that in that first example that we did. So that means that, just think about what the absolute value does in this case. It took all the negatives away. Well, the negatives pop up when n is odd. Okay? All right, so let's think about what's going on. This says that as n gets large, the absolute value gets close to 1/3. All right, so if n is even, well, the absolute value is just that term. So as n is even and large, the terms will be close to 1/3. But if n is odd, then we get a negative value here, and it'll be close to -1/3. So the even terms are going to 1/3, and the odd terms are going to -1/3, which means that the limit cannot exist because limits have to be unique. I can't go to 1/3 and -1/3 at the same time. So the limit does not exist, or another word we could use is the sequence diverges. Here's a graphic representation of what's going on with the sequence. First term is negative, second term is positive, third term is negative, fourth term is positive. Negative, positive all the way. And notice again, we have those even terms are getting closer and closer to 1/3. That's what that dashed line there represents. And the odd terms are getting closer and closer to -1/3. Let's do another example here. Let's do the limit of a sub n equals 4 plus 2 sine n over n. Again, L'Hopital's rule is not going to work here because the top is not going to 0. It oscillates, right? We've got sine n over n goes between -1 and 1, so this just bounces around. Okay, so L'Hopital's rule here won't work. It's not at the right form. And doing our standard division thing doesn't really work either because it's not a polynomial on top. All right, so we recall what we learned back in Calc 1 with the squeeze theorem. If you've got, in Calc 1 it was for functions, general functions. Here we can do the same thing for sequences. If one sequence is trapped in between two, and the outside ones go to the same limit, then the inside one has to go to the same limit. Okay. All right, so let's concentrate on getting the a sub n terms in between two things. Well, I mentioned before that the sine of n here bounces between -1 and 1. So 2 times that bounces between -2 and 2. Add 4 everywhere. We get 2 less than or equal to 4 plus 2 sine n, less than or equal to 6. And now divide everything by n. Don't need to worry about any inequality slipping here because n's going off to positive infinity, so we're not dividing by a negative number. And now look, we've got our a sub n trapped in between two sequences, and those two sequences go to 0. So the thing in the middle also has to go to 0 by the squeeze theorem. All right, so let's look at a specific type of example. This is something that you haven't seen how to find limits before in the past, and this is the idea of a limit of a recursively defined sequence. So this one says it starts at 1, and then as you go up to higher terms, it's in terms of the previous one. So let's show what I mean by that by calculating the first few terms here. So a sub 1 is 1. Then a sub 2, according to the definition here, is the square root of 6 minus a sub 1. We plug in a sub 1, we get 5, so we get square root of 5, which is about 2.236. a3 will be square root of 6 minus a2. We just said a2 is square root of 5. Simplify that, you get about 1.94. This one, a4, is the square root of 6 minus, and then this whole term, square root of 6 minus square root of 5. You get a little over 2. And notice it's kind of bouncing back and forth across the 2 here. It's getting closer to 2. It looks like it's not going off to infinity. It looks like it's going to some number. So let's say that it does, just for argument's sake. Let's say it's equal to some number. Well, then if I look at the very next term, the a sub n plus 1, well, if I start counting at 1, 2, 3, 4, and those terms go off to L, then if I start counting at 2 rather than counting at 1, it's going to go off to the same number as you go off to infinity. So we'll use the recursive definition then. A sub n plus 1 is square root of 6 minus a sub n. Now we'll use our limit laws. I can move the limit inside to the a sub n. That limit was also L, so now I have an equation to solve for L. Get L squared plus L minus 6 equals 0. That factors, and we get the two solutions of negative 3 and 2. Now, noticing that looking at these values here, these are certainly not negative, they're positive. So negative 3 doesn't make any sense. So we have to have that the limit has to be 2. So when you do this limits of a recursively defined sequence, if the limit exists, then you basically are going to set up this type of an equation. And usually the equation is just what you think the limit is equal to the limit plugged into the formula for the next term. All right, so let's just talk about some additional facts for sequences. The first one, in fact, is we've been using it all along. The limit laws for regular functions are valid for sequences. What I mean by that is limit of a sum is sum of the limits, limit of a product is the product of the limits, all of those good things. All those limit laws that you learned back in Calc 1, still valid for sequences. This one we used when we did L'Hopital's rule. If I have a function that's equal to the sequence values for all of the integers, then I can use the same techniques that we used for functions to find limits to get our limit for our sequence. And that's what we did when we did L'Hopital's rule before. And then the last one here we have is that if you have the absolute value goes to 0, then the terms had to go to 0. And we saw that actually the kind of the reverse of that. We had this limit didn't exist and the absolute value didn't go to 0. That was one of the examples we did. This last one here is important for our next section, and this talks about the limit of what we refer to as a geometric sequence. If this base in your exponential here has an absolute value less than 1, then the limit goes to 0. That makes sense, right? If you take a number that's less than 1 and raise it to higher and higher powers, the limit goes to 0. Certainly if I plug in 1 for r, I get 1, no matter what power I raise it to. And if r is equal to negative 1, this will oscillate back and forth between negative 1. If the absolute value is bigger than 1, then this goes off to infinity, or bounces between things getting off to infinity and off to negative infinity. So the limit does not exist.